My project aims to make the Parrot AR drone capable of mapping buildings autonomously. It shows a proof of concept in which the drone navigates to a given goal and builds a sparse map of the environment along the way. This can be useful for investigating and mapping inaccessible environments such as interiors of damaged buildings or caves or even remote asteroids and planets. It even has commercial applications with big names such as CERN and EasyJet already employing drones for automatic inspection. To achieve this, I have studied the famous problem of simultaneous localization and mapping, on short SLAM, from its beginnings to the most recent breakthroughs. Then, I analyzed and compared recent prominent work from 3 different categories and chose the one that gave best results for our system, namely the AR.Drone. Here you can see an overview of the system's architecture, with orange boxes representing modules and green arrows the messages passed between them. We use the Robot Operating System, or ROS, as glue for the software and the Parrot AR drone for carrying out experiments. The piloting module uses the orb's lamp to know its position in 3D space and to get an idea of its surroundings. However, since the hardware only provides one front camera, it cannot determine the scale of its map. This means that it can detect obstacles, but they are arbitrarily far or close. To solve this problem, I introduced an initialization step in which the drone travels a known, specified distance for inferring the scale of the map. Since AR.Drone is optimized to keep the scale from drifting, the autonomous driver can then navigate to a predefined goal. Here I have started the test by flying the drone myself for the initial scale acquisition. Then the autopilot kicks in. In this example, the drone is set to navigate from its start position to each of the tables, landing on the third one to the left. To indicate it has reached one of the goals, the drone hovers in the air for a couple of seconds. In a moment, you will notice a hiccup as a sudden loss of altitude. It was one of the challenges I faced during the development, and it is not related to the algorithms, but rather to the hardware. The drone incorporates a so-to-say smart hovering mode, which is interfering with my autopilot. The test is finished when the pilot detects it has reached the final goal and lands the drone. The navigation accuracy is dependent on the acquired skill, and since this is done manually, it is of no surprise that the landing target was missed by about a meter. The original interface of the SLAM package has limited functionality for inspecting and interacting with the map. Therefore, I have extended it to export the cloud point into a standard format readable by other software. Here, one of our maps is loaded into the widely used program MeshLab, which allows any user to further inspect and, more importantly, refine the map. I have also developed code to infer structure from the map by detecting planes in the generated point cloud through a ransack method. These planes will aid more intelligent drivers to employ a wall-following strategy for navigating the maze. They also offer a higher level structure of the map to compensate for its sparsity. Since SLAM algorithms don't deal well with pure rotations, I made experiments to find a good angular speed for turning the drone. Here we see a couple of them running in parallel. When the rotation is too fast, such as in the top left example, the SLAM easily loses tracking. I have also experimented with raising or lowering the number of extracted features in order to optimize the system. Fewer features mean less computational demand, making it feasible to run the algorithm on board the drone. Finally, I have explored additional methods for navigation based on visual cues different to those present in the map. For example, we can take advantage of the structure of a corridor to detect a vanishing point and navigate towards it. However, if the detection fails, does it mean we reach the end of the corridor and we can safely turn? Probably not. Therefore, this method is unreliable without a direct depth sensor, since the vanishing point is an abstract notion and has no depth associated with it. This concludes my work for the project, but sets up a wide range of tasks for further extensions. Thank you for watching.